Okay, hello. So we are back for another day, another practice test. So let's get all this filled out. As you can see, this is actually the spring 2025. So this is as recent as you can possibly get. I was originally just going to do another fall exam, but it was going to be 2017. And that's a bit into the past, so I decided let's do some spring exams. So let's start off with our first one. Number 1, find the volume of a region in the first octant, so now I know it's going to be a triple integral, that lies inside x squared plus y squared plus z squared equals 9, and above z equals the square root of x squared plus y squared. So let's dissect this a little bit. So we know that x squared plus y squared plus z squared is equal to rho squared equal to 9, which means that now we already know our rho is 3. In the same case, we can see that in this case we can turn this into rho cosine of phi, which is equal to the square root of rho sine phi cosine theta plus rho sine phi sine theta. So we square both sides, which gets us rho squared cosine squared phi equal to rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. So in this case, we can just use our already known trig identities to turn this cosine squared theta and the sine squared theta into a 1. So we just get left with rho squared cosine squared phi equal to rho squared sine squared phi. So our rho's can cancel out, so we get sine squared phi over cosine squared phi equals to 1. So tangent of phi is equal to 1, so we know that phi is just equal to pi over 4, because that would just be square root of 2 over 2 divided by square root of 2 over 2. Cool. Okay. So, oh my lord. No, fine. I'll just keep it. So we already know 2 of our bounds. I'm going to write them over here. We'll go from 0 to 3 and 0 to pi over 4. Now you might be wondering, how do you find your theta? Well, this says our first octant here. If I draw this all out, our first octant is going to be this little area right here, where it's positive x, positive y, and positive z. So we know that if we go this way, well, I guess the z is not really important in this case. It'll just be from 0 to pi over 2. Pi over 2. Okay, so now in order to find the volume of this, we simply, there's not an equation that gave us, so just going to be rho squared sine of phi d phi, sorry, not d phi, d rho, now d phi, d theta. Okay, so let's figure this out. So it goes from 0 to 3. I'm going to take sine phi out. Rho squared of d rho is equals to rho cubed over 3 from 0 to 3, which simply gets you 27 over 3 minus 0, which gets you 9. Sweet. So now we have, evaluating from pi to 4, 9 sine of phi d phi, which simply gets you negative 9 cosine of phi from 0 to pi over 4. So you can just say negative 9 cosine of phi would be square root of 2 over 2 minus cosine of 0 is just 1. So you just get negative 9 square root of 2 over 2 plus 9. Sweet. Okay. So our last integration will be from 0 to pi over 2 of negative 9 square root of 2 over 2 plus 9. Since we don't have any thetas in this case, we simply just multiply it by the theta, which gets you negative 9 pi square root of 2 over 4 plus 9 pi over 2. So in this case, I'm just going to rewrite this. I'm going to rewrite this out to 9 pi over 2 minus 9 pi square root of 2 over 4. And if you take the 9 pi out, 9 pi over 2, you simply, if you substitute that out, you get factor that out, you just get 1 minus square root of 2 over 2. Whoopsie daisy, I want my highlighter, which gets you the answer E. This case, E is our answer. Okay, question number 2. Find this huge integral where r of t is ti plus t squared j plus t squared k from 0 to 1. Now this integral looks huge, but let's break it down, right? So we know that r of t is the vector t squared, and t squared. So in order to find this, r of t, we got to do f of r of t times the magnitude of r prime of t. So we know that r of t is this, so r prime of t in this case is just 1, 2t, 2t. So if you find our magnitude, that would simply be the square root of 1 squared plus 2t squared plus 2t squared. Gets us 1 plus 4t squared plus 4t squared, all square root, which just gets you the square root of 1 plus 8t squared. Okay, in this same sense, if we plug in r of t to f, you get, so this is x, this is y, this is z, remember? So you get t times t squared times t squared. This is all under the 5th root, which gets you root 5th t to the 5th, which simply just gets you t. And then what goes underneath that? Well, that's just 1 plus 8 times y, which in this case is t squared. So in this case, we just get t over the square root of 1 plus 8t squared. That's our f. We need to multiply that by our magnitude of r prime of t, which is just 1 plus 8t squared. If you notice this, the square root of 1 plus 8t squared is on the top and the bottom, so we cancel that out. And you simply just need to evaluate the integral of 0 to 1 of t dt, which just becomes t squared over 2 from 1 to 0, which is just 1/2. 1/2 is f, which is our answer. All right, so number 3, compute the double integral 3xy squared over 1 plus x squared dA, where r is this rectangle here. Okay, so what we're going to do right now is we're just going to set up our integral. So I'm actually going to evaluate from y first, so it'll go from -2 to 2, 0 to 1, 3xy squared over 1 plus x squared dy dx. So I'm going to take the 3x over 1 plus y squared out, 1 plus x squared, -2 to 2, y squared dy, which simply returns you y cubed over 3, -2 to 2, which gets you 8 over 3 minus -8 over 3, which gets you 16 over 3. Sweet. Now, we're going to evaluate from 0 to 1 of 3x1 plus x squared dx. Remember, the 16 over 3 is still there. Okay, so, whoops, not that. We're going to do a bit of u substitution, where u is 1 plus x squared. du, in this case, would just be 2x. Now, this is kind of weird. In order to get this, we got to do 3x multiplied by 2 over 3, which just ends up with 3 over 2 to cancel it out. 1 over u. In this case, the bounds would be 1 plus 1 squared is equal to 2, and 1 plus 0 squared is equal to 1. Okay, so when we integrate this, we get 3 over 2 natural log of u from 1 to 2, which simply gets you 3 over 2 times natural log of 2 minus natural log of 1. Natural log of 1 equals to 0, so we don't keep that. And then you simply do 16 over 3 times 3 over 2 natural log of 2, which just simply gets you whoopsie daisy. Oh wait, sorry. Yep, my bad. Had a brain fart there. 3's cancel out, so you get 8 times natural log of 2. 8 natural log of 2, which is our answer D, which is our answer for number 3. Cool. Okay, this number 4. Use Green's theorem to evaluate this integral, where C is the boundary of the rectangle with vertices C's 0, 0, 1, 0, 1, 3, and 0, 3, oriented counterclockwise. So let's first draw out this rectangle, shall we? It goes from 0, 0, 1, 0, 1, 3, whoops, 1, 3, and 0, 3. Sorry. There you go. There's the triangle. Sorry, not triangle, rectangle. This very cool rectangle right here. Okay. So, what is Green's theorem, you might be asking? Well, in this case, this is our F, right? This is our G. Our F, our G. Green's theorem simply denotes that our F, sorry, not our, that F, our big F, will be equal to the partial derivative of x at G minus the partial derivative of y at F. So if you see the partial derivative of x at G, it's just 0, there's not an x in there, but the partial derivative of y at F would be 2x, which gets us to x. And our bounds are super simple. If we evaluate x, it'll be simply from 0 to 1, and from y will be from 0 to 3. dx dy. Okay, so we can evaluate this now. This will become negative x squared from 0 to 1, which equals to negative 1 minus 0 equals negative 1. And then from 0 to 3 of negative 1 dy, you simply get negative y from 0 to 3, which simply returns you the answer negative 3, which is B in this case. Yep, that's our correct answer. Cool, that's Green's theorem. Number 5, let D be the region between x squared plus y squared equals 1 and x squared plus y squared equals 4, which is above z equals 0 and below z equals 4 minus the sum of x squared plus y squared. Using cylindrical coordinates, we know they give us our f. What is the value of this volume? Okay, that was a lot, but let's break it up. Okay, so we already know that x squared plus y squared equals r squared. Y squared equals 1, which means that r is equal to 1. And in this case, it's the same thing. R is just equal to 2. So in this case, our radius is not from 0 to a number, like usual. Now it's from 1 to 2. And we know that our z is above 0, so that's our lower bound. And in this case, our z is equal to 4 minus r squared, which is our upper bound. And for our theta bounds, we simply know that it is a circle. So 0 to 2 pi. 1 minus r cubed, which is multiplied by r dz dr d theta. Okay. Whew. So if we go from 0 to 4 minus r squared, I'm going to take this out. This actually becomes, whoopsie daisy, dz. That simply becomes z. from 4 minus r squared 0, which just gets us 4 minus r squared. Now, when we multiply that times r over r cubed, is just 1 over r squared. We get 4 minus r squared over r squared, which I'm going to split up into 4 over r squared minus r squared over r squared, which just gets us 4 over r squared minus 1. Okay, now our radius bounds are from 1 to 2, from 4 minus r squared minus 1. So in this case, I'm going to say 4r negative squared, which gets us 4r negative 1, which simply returns us negative 4 over r. This just becomes a negative r. That's from 1 to 2, which gets us negative 4 over 2 minus 2 minus negative 4 minus 1, which gets us negative 2 minus 2 minus negative 5, which gets us negative 4 plus 5, which is 1. And then from then on, from 0 to 2 pi of 1 d theta simply gets us 2 pi. So in this case, our answer is E, which is 2 pi. That is correct. Okay, so considering the following integral, which of the following is the correct way to rewrite the integral with respect to the order integration dx, dz, dy, and the original integration order was dz, dy, dx. Now, I recently thought of this, and I'm going to teach it to you guys because I think it's helping me out a lot. See these integration things right here? We're going to go backwards a little bit. So we know that in the bounds of x, it's simply just going to be x. For the bounds of y, it's going to be y of x. While for z, now it's going to be z of x and y. It's holding all of those. So the same logic applies. When now it's x, when now it's y, we know it's y. Z will be z of y, and x will be y and z. So x should just contain a y, right? So in this case, if we look at our original z bound, z should contain y. Z, in this case, doesn't actually change. It stays as 2y to 4. So in this case, we can take out a few answers. It wouldn't be C, and it wouldn't be B. But let's look at this the other way, right? So now we don't have to really worry about Z. So let's just, oh my lord, I need to really start using the other eraser. Okay, let's just focus on x and y right here. So this is our y bound, this is our x bound. Now that x goes from 0 to 2, while y goes from the line y equals x to y equals 2. So let me use a different color for this. Okay. So in this case, y goes from x to 2. So let's flip the integral, right? We know that 0 is less than x, which is less than 2. 0 is less than, whoopsie daisy, x is less than y, which is less than 2. So that x is equal to 2, the same way that y is, not 2, x is equal to y, just like how y is equal to x. So if we rewrite it now, going like this instead, the new x bounds will be from 0 to y, and y will simply be from 0 to 2. So let's see which ones follow that. Let's see, our y goes from 0 to 2, but our x bounds go from y to 2. Can't be A. For D, goes from 0 to 2 here. Can't be that. 0 to x, definitely not that. So the only answer can be is F. which is our correct answer. Cool. 7. If the gradient phi is equal to the vector 2x, comma, minus 2y, then the I'm not saying this. Equipotential curves, which are the level curves of phi, are mostly... Okay, so let's look at this now, right? You might be wondering, how do I even do this? Well, this is actually simply just find the potential. So we know how to find the potential, right? This is our f, this is our g. Simply find the integral of fx, which in this case would be x squared plus some constant. Then we simply take the derivative at y, which gets us 0 plus a prime of y, which is equal to our g, which means our a prime of y is equal to negative 2y. Now, all you have to do now is just integrate both sides for y, which gets you a of y, this constant, is equal to negative y squared, which means our potential function is x squared minus y squared. Now, how do you find the level curve? Well, that's simple. You have your equation here, and you set it equal to a constant. It can be a k, it can be an n, it can be an a. If you have it as a z, remember that z is a constant, not z. So, in my honest opinion, you should just set it equal to a k. So, if we look at this now, you might be like, what's going on here? Well, just look a bit closer, right? This is the standard form for a hyperbola. In this case, 7 is the hyperbola, which is our answer. Okay, compute the double integral x dA, where r is the region in the plane inside the circle, x squared plus y squared equals 4, and the line y equals negative x. So they were very nice enough to give us this picture here, which I'm very grateful for. But let's churn this out, right? So we know that r squared is equal to 4, which means that r is equal to 2. In this case, r is equal to 2. And we can solve our theta. Y is equal to r sine of theta, while x is equal to negative r cosine of theta, because this is negative. Okay, so in this case, you could say 2 sine of theta is equal to negative 2 cosine of theta. So sine of theta over cosine of theta is equal to negative 1. In this case, the theta would be equal to negative pi over 4, as seen right here. Now you could evaluate the entire integral, but what I'm going to do is I'm just going to evaluate half of the integral and then we'll multiply it by 2. So, because I'm lazy. So I'm just going to go from negative, oops, that shouldn't go there, from 0 to 2, negative pi over 4 to regular pi over 4 right there. And I'm just going to do x r dr d theta. Sorry, not x. X in this case is r cosine of theta times r dr d theta. So r squared cosine of theta bound between 0 and 2 dr will simply become r cubed over 3 from 0 to 2, which gets you 8 over 3 cosine theta. Okay, and then our last one, from negative pi over 4 to pi over 4 of 8 over 3. Oh my lord, what the heck just happened? Oops, 8 over 3 cosine of theta d theta. You simply get the integral 8 over 3 times sine of theta from negative pi over 4 to pi over 4, which returns you the answers. 8 over 3 multiplied sine pi over 4 is square root of 2 over 2, minus sine negative pi over 4 will be negative square root of 2 over 2, which simply gets you 8 over 3 times 2 square root of 2 over 2. So in this case, we got 8 over 3 times square root of 2, I guess, over 1. So 8 square root of 2 over 3. And then remember, that was only half of the integral. That we only covered that half, so we got to multiply it by 2, which just gets you 16 square root of 2 over 3. Wait, I think I've done something wrong here. I believe I've done something wrong here. What did I do wrong here? Oh, I see it. Okay. So I'm just going to multiply it out. 16 square root of 2 over 6. Wait a second. That's very confusing me. What did I do here? Huh. This is quite strange. Huh. I think I've kerfunkled. Okay. Oh, this is certainly quite strange. Okay. I imagine what happens in this case is I simply just have to evaluate to 3 pi over 4. Which in this case will get me all the same answers as r cubed over 3 from 0 to 2 gets you 8 over 3. 8 over 3 cosine of theta from negative pi over 4 to 3 pi over 4 will get you 8 over 3 sine theta from negative pi over 4 to pi over 4. Which gets you 8 over 3 pi over 4 is just square root of 2 over 2. Minus negative square root of 2 over 2 gets you 8 over 3 times 2 square root of 2 over 2. Simply gets you 8 square root of 2 over 3. Ah ha ha. Okay, ladies and gentlemen, do not do what I just did. Just evaluate the entire integral instead of trying to play it smart. I wasn't saving that much time anyways. Instead, just do the integral from negative pi over 4 to 3 pi over 4. I promise it works out, and I think I probably did my math around somewhere, but yeah, 'tis happens. Okay. Moving on to question number 9. Question number 9 is another question where you have to use the fundamental theorem of line integral. So that's just the potential function at b minus the potential function of a. Okay, so let's find the potential function, shall we? So we know that the integral of f of x is just equal to will be equal to ey cosine of x plus a of y, and then d over dy will just equal out to ey cosine of x plus a prime of y equals to g, which is e to the power of y, times cosine of x, which means a prime of y is equal to 0. So in this case, you know that our potential function is just e to the power of y times cosine of x. So if we take that at b, b is 0, 1, and a, which is 0, 0, you get e to the power of 1 times cosine of 0 minus e to the power of 0 minus cosine of 0, which gets you e times 1 minus 1 times 1, which gets you e minus 1, which in this case is our answer A. Whoops, forgot to do number 8, smiley face. Number 9, the answer is A, e minus 1. Then number 10, find f of xy equals negative yi plus xj, where c is the circle of radius 1, centered at the origin and oriented counterclockwise. Okay, so how do you parameterize a circle? Well, simple. It's just cosine t, comma, sine t. And our radius is 1, so it's just multiplied by 1 for each. If our radius was 2, it would be like 2 cosine t, 2 sine t. And our f is the vector negative y, x. This is our r of t. So in this case, in order to find this, we got to do f of r of t times r prime of t. R prime of t in this case is negative sine t cosine t. And our f at r of t is simply equal to negative sine of t for negative y, and x is equal to cosine t. So once we do f times r prime of t, you get negative sine of t times negative sine of t plus cosine t, spoiler, times cosine t. Get you sine squared t plus cosine squared t, which is simply equal to 1. So we know it's a circle and it's oriented counterclockwise, so we know the bounds are from 0 to 2 pi of 1 dt, which means the answer for this one is also simply 2 pi, which is f, and we get a smiley face. Sweet. Last 2 questions. Compute the double integral 1 over x natural log of y dA, where the triangle is a triangle with vertices 1, 1, 1, 3, and 3, 3. The hint is that, oh my lord, my computer just went, is that the integral is easier with one order of integration than the other. Let me turn my computer all the way down. Is easier with one order of integration than the other. So let me draw out this triangle, shall we? It goes 1, 1, 1, 3, and that's about 3, 3. Okay, so in this case, I'm just going to tell you guys, but the order of integration is easier in this question when you go x first and then y. Why? Well, in this case, x will go from 1 to this line here. This line is just equal to, if I wrote it in y, it would be y is equal to x, because then it would just extend right here. So in this case, x is just equal to y, so your bounds would be from 1 to y. Your y bounds would just be from 1 to 3. And then this cool little trick you can do, so you can simply say, instead of evaluating 1 over x times natural log of y, you can just say 1 over x times 1 over natural log of y dx dy. So you take the natural log of y out from 1 to y, 1 over x dx. That simply integrates into natural log of x from 1 to y, which gets you natural log of y minus natural log of 1, which, as we all know, is equal to 0. So we multiply it back in, where natural log of y over natural log of y is just simply equal to 1. So now our integral is simply from 0 to 3 of 1 dy, which gets us y from 1 to 3, which is just 3 minus 2, not 2, minus 1, which gets us the answer 2, which in this case is B. That is number 11. Last question. Finally, this is a Lagrange multipliers question, our favorite types of questions. Compute the absolute maximum of the function, where they give us our f here, they give us our g here. So standard operating procedures here, we take the gradient of f, in this case is 2, 2, negative 1, and then we take the gradient of g, which in this case is 2x, 2y, 2z. So now we set the gradient of f equal to lambda times the gradient of g. So 2 is equal to lambda 2x, 2 is equal to lambda 2y, and negative 1 is equal to lambda 2z. So I'm going to evaluate x and y first. If we multiply this, the 2's cancel out, and the lambda 2's cancel out, which seems you just get 1 over x over y, which means x is equal to y. This is very important in the future and a very good trick for this question. So now I'm going to evaluate 2 equals lambda 2y over negative 1 equals lambda 2z. So in this case, the lambda 2's cancel out. You get negative 2 is equal to y over z. Means that y is equal to negative 2z, which means that x is also equal to negative 2z. So we plug it back into our constraint, Rg, which you get negative 2z squared plus negative 2z squared plus z squared equals 9. So that gets you 4z squared plus 4z squared plus z squared equals 9, which equals z squared, 9z squared equals 9. So that z squared is equal to 1, and z is equal to plus or minus 1. So we simply evaluate that. So when z is equal to negative 1, y is equal to negative 2 times negative 1, which equals to 2, which means that x is also equal to 2. In this case, our critical point will be equal to 2, 2, negative 1. And whenever z is equal to 1, y is equal to negative 2, which means that x is also equal to negative 2, which means that in this case, our critical point is negative 2, 1. Okay, so we have our critical points now. So let's just evaluate them into the f equation. So 2, 2, negative 1, that simply gets us 2 times 2 plus 2 times 2 minus negative 1. Gets us 4 plus 4 plus 1, which equals to 9. And then f of negative 2, 1, equals out to 2 times negative 2 plus 2 times negative 2 minus 1, which equals out to negative 9. So in this case, our absolute maximum is 9, which is B, which is our answer. So that was the most recent exam. As you can see, it was a little bit, I think it's a little bit easier than the other ones that we've done so far. I'm very sorry we're having the question 8 when I did it. I guess my trick just had some little algebra things that I missed. But in this case, just evaluate from from negative pi over 4 to 3 pi over 4. Don't try to do what I did. Wasn't that bad. Honestly, I think the hardest question here was maybe this. If you didn't understand what they were asking, all the other things were pretty easy to get if you knew all the concepts well, and they tell you what to do. Actually, 11 was also pretty tough if you didn't know what you were doing. But overall, I think it's a very good thing, and if you made it through with me, I hope you got a little bit better at your Calc 3 today. Good luck on your exams. I definitely need good luck on my exam. It's coming up, so honestly, me doing these practice tests is just extra practice. So I hope you learned something today, and have a good day.